feasible it would be on a hobbyist tier project such as this. On the other hand, push back, and this is where we're going. But before I get too ahead of myself, in case you aren't familiar with the open source smart glasses, it's a design for smart glasses that's completely open source in both hardware and software, at least the parts that we can control, with the main goal being to create something that's actually immediately useful out of the box to users and even just developers in general. As for software, it ran on the Wearable Intelligent System Android app that would act as something of a head unit and would provide a bunch of smart glasses apps immediately, such as live translation. You all know what that is. Live captioning, which basically subtitles in native language, mainly useful for people who are hard of hearing or deaf or otherwise, and even a contextual search engine, amongst other things. Now, again, my job was to find not only the workable, but attainable and affordable hardware for the OSSG to use, as well as write the software for it. It turns out that was harder than I originally thought, because I couldn't just go back to using that same display that I used in the telescope that's very easily available off the shelf, because that was way too bulky, not suitable for everyday use. So we needed something better. But to get something better, you need to go through a supplier. And unfortunately, suppliers don't like shipping in small quantities to random hobbyists such as myself. They want to ship in bulk, right? So the problem became, okay, how can we convince them to ship in small quantities to hobbyists? And the answer to that is you have to convince them that you are a real company. And fortunately, I still had the domain name and the website and the email address to a startup I had tried co-founding some years prior. I was able to convince the supplier in China that, hi, I am a legitimate business trying to do some like product development research. Please ship us some samples. And they said, all right, let's do this. After that, we got the sample unit in the mail. That's what you're seeing on screen right now. And the problem became, what do you do for software stack? Well, once again, I couldn't use the same software stack that I had used on my original telescope device because that had some very heavy limitations. It was capped at something ludicrously small, like a 240 by 200 screen resolution and this extremely limited 8-bit color palette. It was just not workable for a text-based device. So I needed to do some more research to find something else. And what I had found is that as of today, sort of your best option for doing composite video output on an ESP32 is to use a combination of two different libraries. First one being called Lovian GFX, which handles the composite video output from the ESP32 microcontroller. And the second one being called LVGL, which you're probably familiar with if you're in the embedded world. It's a graphics library for microcontrollers and handles all the mundane parts of essentially building a UI. Of course, we had a ludicrous number of technical difficulties along the way while doing this, particularly when it came to memory management. You have to understand that Lovian uses memory, LVGL uses memory, our microphone was using memory, Wi-Fi was using memory, and if you've ever worked with an ESP32, you would know that it has very, very little memory. So we had to spend quite a lot of time getting that all jam-packed in there and stable. But once we did, it was smooth sailing, and it was really, really great because you're able to display these awesome UIs like you see right here, all from an ESP32 microcontroller, which is great because they're just so cheap and accessible. And just as a side note, before I move on, I just want to say if that you're ever interested in personally developing your own ESP32-based smart glasses system using a composite display such as this one or the one with the telescope, you should because it's the cheapest way to do it. I've broken out all of our relevant display code from the open source smart glasses into its own library. Link at the top, otherwise just ask me later, I'll give you a link if you've forgotten. So you can play around with it, tinker, do whatever you want with it, turn it into its own project. And the best part is for this, you don't even need an expensive micro display to get something working. Really, all you need is one of these composite to USB capture cards. You can get them on Amazon for 10, 15 bucks, and that's all you need. Plus, it's just the best way to develop on these in general, as opposed to make a change and then squint into your little viewfinder. So that's really all you need to get started. Now, once everything was sort of complete for the most part on the open source smart glasses front, Caden and I went to CES in Las Vegas in order to show off our glasses, get feedback from people, and potentially even find some contacts within the smart glasses industry. And of course, nothing is ever really sunshine and rainbows. We had some OSSG units get dinged up on the plane right there. So that first night in Vegas, we had turned our hotel room into this goofy little workshop where we just worked all night trying to get these glasses fixed in time. And we did, and from there it was all smooth sailing. To the point where we were actually able to get private demos with a bunch of different companies. Vuzix, Avegant, and Colorchip were sort of the main highlights of those. And what we learned from all of these demos really surprised us. Now, in all of these demos, what we saw is that these companies had wonderful, wonderful hardware, leagues better than this. But what they didn't have was software. In fact, all of their demos were still images, a slideshow maybe. I think a couple of them had like a little like animation of like navigation going, but there was no real software on any of these glasses. So we realized, okay, there's this massive gap in the market. There's this need for software for smart glasses. But wait a minute, we already have that. It's called the Wearable Intelligence System, which leads us to today, in which we've sort of stripped down the Wearable Intelligence System to its necessary guts and transformed that into what we have tentatively called the Smart Glasses Manager, which is going to reduce the time it takes for developers to create apps for smart glasses by a ludicrous amount, by making it so we essentially have a middleware for a smart glasses developer to go through and then have all the connections between all of the individual commercially available smart glasses just handled for them right out of the box. There is much to be done on this front, so stay tuned for more details. Thank you.
Awesome. Thanks a lot, Alex. That was a great presentation. I definitely have some questions that we'll get to in the Q&A. And I think Patrick is probably ready. So our next presenter is Patrick Chwalek, who needs no introduction because he already had one. And so, yeah, please take it away.
All right, let's see if this works this time. Let's see. Can you guys see my screen?
Yes.
All right, great.
Looks good.
So hi, I'm Patrick. I'm part of the MIT Media Lab in the Responsive Environments group. And today I'll be talking about Project Captivates and AirSpecs, which is the next version of Project Captivate. So as Caden talked about, my background is in embedded systems, hardware and software. Although prior to the Media Lab, I was a mechanical engineer and then worked at Lincoln Laboratory on defense applications or defense projects. And then going forward, I'm going to be working more on National Geographic projects. So it's kind of all over the map. But embedded systems, hardware and software is really the running theme. And responsive environments at the Media Lab, we are focused on hardware systems and visualizations of the data coming from the hardware system. So we have projects where we deploy sensors out in a recovering cranberry bog, and we virtualize the entire cranberry bog into Unity, and then so you can kind of walk through it and see the different sensor values and how the atmosphere actually physically changes. So it's kind of a digital twin of the space. And then we're also doing a lot of space-related research, so sending stuff up to the ISS or to the moon. And then I'm focused more on glasses right now and human comfort and perception, and then shifting to more animal sustainability related projects for this next year and a half. But what I want to talk to you guys about is first Project Captivate, which I started 3 years ago, right before COVID. And the reason I started this project, so I started with another PhD candidate in the group, David Ramsey. We started getting frustrated because coming from like sensor and hardware backgrounds, we started diving into HCI research and finding that a lot of it is really a bunch of controlled experiments in a lab environment, right? And so when you try to recreate that experiment out in the wild using commercial wearables, it doesn't really work all that well for a variety of reasons. Again, when you have sensors in the wild, the signals will just look different. You have noise artifacts. It just becomes a more complex problem. But also commercial systems, which are often used for like research applications like, Apple Watch or Empatica E4s or All of them, really. They don't really give, it's like a black box within a black box. So they tell you what kind of sensors they have. They don't really say how they condition the sensor signal. If you're using Apple devices, some of the sensor information is temporally variable. So like you might get a heart beat measurement every second. Sometimes you might get a lag of about a minute. And commercial companies really do this because they want to give you data that they know is valid. But for researchers, we care about accuracy, but we also love seeing the raw signals because that allows us to build more complex models. That if we create our own sensor system, we could use those models instead of kind of building a model on top of already an abstracted sensor signal that doesn't really scale well if you want to put it to a different piece of hardware. So we started Project Captivate. This is the very first version of it 3 years ago. It was just 3 PCBs, rigid, no hinges, but it kind of did what we wanted it to do. It was a system that collected phase temperature measurements, had an IMU on board, so 9-axis inertial measurements, a bunch of LEDs, just really the basics, but it was like the simplest design that we could build that was cheap. The issue with this is we ended up going to China for like a month, and we met with a lot of manufacturers about how we could scale this, how we can make it cheap. And all of them pretty much said you need a hinge because just transporting this thing, it's very fragile without one. But also they gave us so many other feedback about how to turn this more into a product, which we really weren't intending on going at that point, and then eventually just evolved into what it is today, which I'll get to. But one of the biggest problems with smart eyewear is hinges. Anyone designing open source hardware or even commercial grade hardware know that electronics through a hinge is a pain, really, because you have either wires going through there or a flexible circuit. And if you put enough dynamic bending, on these pieces of circuitry, they will crack. It's just physics. It's going to break. And so the idea here is you need to create the hinge design as robust as possible. And so we spent a while buying a bunch of different smart eyewear that we could find in the Shenzhen electronics markets, and taking them apart. And we found that a lot of them aren't designed all that well, and they're not really meant to live past a year. And so we spent a lot of time working on this. We even found this one stall where this guy who's had the stall for 30 years, he just sells connectors. And so we really wanted to find a connector that both had act like a mechanical hinge, but also gave us the electrical contacts for any position. And we ended up finding that Molex did create a hinge connector device in the 90s. But they discontinued it shortly after because of low demand. So anyways, if you're creating an electronic hinge assembly, there's a market for it. I don't know who would buy it, but I definitely would. So we also spent a while thinking about light pipes because people like LEDs. And so we made sure to integrate LEDs into our glasses. We also thought about using the glasses for concert performances. So if you put these glasses onto the audience, the performer can actually actuate the audience. All the glasses are equipped with a radio that can do mesh networking. So the performer can get some idea of how people are kind of in tune with the music, and then they could kind of actuate different people in different ways with colors and also LED positions, which I'll talk about in a moment. And so this is one of the early designs of the glasses where we're playing around with a bunch of different LEDs. You can see the light pipes at the very top. They're being lit up by these side LEDs. We also have some LEDs that go towards a person's eye that work for notification, but also to kind of mess with a person's attention, because we're really curious on measuring attention across contexts and how to kind of mess with people too a little bit. And then there's also 2 other LEDs which aren't shown, which are forward facing, which a user cannot see, but it leads us to do some cool like interaction experiments where you're talking to someone and your LEDs kind of alert the user you're talking to about something, but they don't necessarily alert you. And so a lot of the assembly of these glasses has been done in-house at the Media Lab, mainly by me. And so there's a lot of intricacies, which I won't go into because of time. But when you're building these open source hardware, there's always a trade-off between what you're going to 3D print to what you're going to injection mold, how much funding you have, if you can invest in tooling. There's a lot of factors that kind of go into play, and that's kind of where I get to flex some of my mechanical engineering degree from years back. And then this is the final pair of Captivates. The main, well, I guess I really didn't talk about this, but the main idea behind them is we wanted to create a system that's sensor rich, that allows researchers to collect as much data as they can without making people feel socially insecure of wearing them. Because if we want to, convince a bunch of users to wear them so we can collect their data, they don't necessarily want to wear things that look a little out of the ordinary or a lot out of the ordinary. So that's why we created this whole new version without anything that looks too crazy, and we kind of adopted like a Ray-Bans-esque like aviator look to them as well. And we did also make lenses for them too, although I generally don't put them in because I don't wear glasses. But so this is the latest design, the latest of Project Captivate. Project Captivate also had a bunch of sensor subsystems, LEDs, inertial measurements. It was getting temple and nose temperature, because we found that there's one study 5 years ago which showed that nose temperature decreases as a function of cognitive load. So the more you're focusing on something, your nose temperature decreases, but your temple temperature actually stays stable. What's also not listed here is we're also looking at your blink activity. So for one eye, if you're blinking or not, because that's very context dependent. If you're reading a book or talking to someone, it's also interesting to look at blink across two glasses that are used by users that are going through a social interaction. So you can look at things like physiological synchrony. So when you're talking to someone, if you're really in tune to the conversation, your head is kind of bobbing along with the other person, like a professor or a lecturer or just your friend. But also the blink frequency can also be matched as well. So there's a lot of things to explore there. We also used the existing Vive system. So Project Captivate had 3 diodes on each face, one on each face, and we're able to use existing Vive infrastructure to get 3D location of where you are in a space. The idea behind that was we wanted to, again, in a concert environment, figure out where each user was, and then actually based on location as well. We didn't actually end up doing that because of COVID, but it was a feature that we played around with. And they are fully open source in the end. So, actually, before I get into the open sourceness, we created a quick dashboard, which is pretty ugly, and I'll show you a new one that we've designed for AirSpecs. But this kind of just shows you all the sensor signals streaming, and a couple things that you can kind of play around with as well. And it is fully open source. So on captivate.media.mit.eu, there are all the design files, and there's a how-to guide of how to assemble it, a bunch of feature documentation, and et cetera, et cetera. And then I pivoted a year ago into doing more building-related research, so measuring people's comfort across contexts. So I was really interested in really figuring out what makes a person comfortable in a building, outside, just in general. We're talking about physical comfort, but also internal comfort. And they're kind of interrelated, because if you look at, not to get too far into the weeds, but if you look at like flow state research and things like that, when you're very invested in a task, you don't necessarily think about how uncomfortable you are until you kind of snap out of it. And then you start thinking about, maybe the air is too dry or too hot in the space and things like that. So really designing a platform to kind of measure people's subjective comfort across context, but then also using all the sensors to get quantitative measurements, and then building a more individualized model of a person's comfort that then the glasses can then inform a building to then actuate for that individual user for where they are. And so we built AirSpecs. So AirSpecs, similar design to Project Captivate, but I just threw a bunch of sensors on there, a bunch more. So looking at gas sensors, we're looking at volatile organic compounds, nitrous oxides, carbon monoxide. We're looking at humidity as well, temperature, ambient. We are looking at light levels and light color. because depending on what kind of light you're exposed to, that could lead to different melatonin levels in your body. So how sleepy you might be, or how engaged. We also added a lot more temperature sensors. So now our skin temperature sensors. So now there's 5, all of which are factory calibrated. So they're digital temperature, non-contact temperature sensors. We have an IMU on board as well that can sample at a faster rate than the previous version, and a bunch of other stuff. And we're looking at new ways of also showing people new types of visualizations using the glasses. So here you could see a Unity visualization of how a person can kind of wear them and see how the environment changes around them. We're also looking at new types of user interfaces with the glasses. So I partnered with a PhD student at the University of Fribourg in Switzerland. We're designing this new type of interface to kind of give a average user a summarized a summary of the information of the environment they're seeing, of the environmental characteristics that they're exposed to currently, because we find that it's an interesting teaching tools, right? So like one example is if you're at home and you're cleaning your house with a cleaning agent, right, that exhausts some kind of volatile organic compounds. Users don't generally know that that's bad for you. They could smell it, you could smell bleach and things like that, but you don't really know how that's impacting your health. And so the idea here is we could design a system that a user can wear throughout their day, and also that not only measures the user but also measures the environment, and gives users the tool to kind of reflect back on their day, their environment, how they're feeling, and what could be the cause of any kind of significant fluctuations of how they're feeling, or their health, that is. And we are building 20 of these new versions, which is called AirSpecs, which we're going to be deploying for a user study across Boston, Fribourg, which is in Switzerland, and then in Singapore. So in Singapore, we've partnered with with the University of Singapore, who there's a lab there that does comfort research, and so we're partnering with them to build out this app even further, so that we could better assess a person's subjective comfort and then relate it back to all the signals that we're collecting with the glasses. And that's it. So yeah, that's kind of a quick dive into the things that I'm doing here at MIT. And yeah, I think we're open for Q&A.
Awesome. Yeah. Thank you so much, Patrick. That was very cool to see even more in depth everything that you're working on. And yeah, like Patrick said, we're diving right into Q&A. So feel free to ask your questions. If you have a question, you can just unmute yourself and ask. You can put it into the chat. You can give me a ping. But yeah, go right ahead. Ask Alex and Patrick whatever questions you have.
Yes, thank you for the presentation. It was awesome. It's Max here. I had a question to Alex. At which stage of the development do you think you can integrate the cameras into the smart glasses for like maybe object recognition, like a computer vision and stuff?
So currently at this stage, like I said, we've sort of moved on to developing the smart glasses manager. So I don't see us integrating a camera personally ourselves. And also a big problem with that is we are restricted when it comes to composite video output, right, which is what this uses. You are restricted to pretty much just the plain old ESP32, or in our case, ESP32 Pico D4, which doesn't have a MiFi connector for a camera. I don't know immediately of another way to integrate that, just because it's not something we really look into all that hard. Definitely look into it yourself, but that's not really something we've explored too much. Sorry, that's not the answer you're looking for.
I mean, it's worth mentioning that the ESP does have a camera integration with the ESP cam. Now it uses a huge number of IOs, probably more than we could actually handle right now. And the power usage is already fairly high, and so you add a camera, fairly inefficient, and it's using one of these like OV style cameras, which unfortunately have a very long like shutter length, and so as you're moving on your head you get shearing, and so it's not really a great experience. So I would usually you're seeing cameras in more application processor based glasses, which are kind of heavier in terms of compute and power, So I think it could be made to work. We're probably not adding that anytime soon, though.
Okay, thank you, guys.
Well, I have a question for Patrick. I was interested in your choice of sensors and also what you think you like if you were going to add more sensors, what they might be. So you have a ton. Well, you have a ton of sensors in there, but they're kind of not the first thing that many people think of when they think like you're trying to measure physiology. People might list like okay, PPG and EDA/GSR, or maybe even like some brain sensors like EEG or FNIRS or something if you're on glasses. But you're going for like a different suite than most people are thinking of. Like, I mean, gases for one thing is pretty novel, and also like really heavily relying on temperature. So, what's the thought process behind those choices?
Yeah, no, that's a great question. So I've been building sensor systems for close to 10 years now, and when you're doing wearables, FNIRS, um, which anything electrode based, for example, is hard to do for like ambulatory measurements where you're on the go because you get a lot of noise artifacts. And if you look at any research for electrode based sensing techniques, a lot of it is how to remove those noise artifacts. And so, and if you look at any commercial system that does EEG that's on the go, or anything that's electrode based, they heavily rely on user calibration. And when you're calibrating the device, you're kind of sitting in your chair, you're calibrating it, and then you perform an activity that then gives you some kind of a deciphered measurement, some kind of index of like your attention or your focus or anything like that. But then once you start moving around and sweating, the impedance changes, right, of the whole like sensor infrastructure, and so you would need to do constant recalibration. So the first thing is that's why we didn't do anything that's electrode based. Also, with electrode based techniques, you need pressure. And for glasses, if you talk to anyone that wears glasses, they don't like pressure, especially around the nose, because it could lead to migraines. Um, for FNIRS, it's similar too, because FNIRS is great until you start introducing a lot of motion in the glasses. Then the signal starts changing a bit, and you then it just becomes a pain. So for skin temperature, for instance, which we're doing non-contact skin temperature measurements, that doesn't change too much when you're talking about measuring at one specific location and then a millimeter from that original location. Temperature is a very slow signal. And so that's why we kind of chose that. For the new design, for AirSpecs, we added a bunch of connectors. So this is one pair that I have with me.
Nice.
So we added a bunch of connectors on the side to allow people to add on their own sensor subsystem. So like this one, you could see I added on a PCB that I designed with a speaker. And so we're looking at
Cool.
beta EEG synchronization, beta brain signal synchronization to a stimulus. So I'm flashing a specific stimulus at a person's eye using my built-in LEDs, and then also coupling it with the speaker, we're synchronizing a chirp to that frequency as well. And then we're able to study a person's brain signals with an additional EEG system. And that's the way I envision our system being used. This is the base platform. You could add on more sensors if you'd like. And then if you want to do electrode-based sensing in a controlled environment, you could use a EEG headband or EEG just raw electrodes. We find that that's probably the best thing to do. But yeah, I mean, at the end of the day, we chose the sensors that we chose just because they offer the most robust signal across context, and they're not particularly high power. So we don't have any displays or cameras. Because if we added that, then the system would become a lot more complex. I would have to switch to a different microcontroller architecture entirely, and it'll be difficult for me to rely on Bluetooth anymore. I would have to go to Wi-Fi or something like that if I want to transmit raw video. So anyway, that was a long-winded answer, but
Cool.
that's
It's
kind of why
very,
we did
very
what we did.
helpful. I think, it's there's a lot of trade-offs there that you have to consider to make something you can wear all day that you can handle the noise. There's another question for you, Patrick, in the chat. Wondering about you're talking about 3D space recognition where the glasses are recognizing their position. And they're just wondering maybe some more information about how that works and what you're looking at using it for in the future.
Yeah, so we had that working about 2.5, 3 years ago with the original Captivates. Again, the idea there was before COVID, we were going to partner with the House of Blues in Boston and put this on to at least 30 users, and then have all the glasses meshed together and do like a performance where the performer gets the raw signals of the glasses and then also knows the location of each pair of glasses, and they could trigger the LEDs based on location of the users. Um, so we had that working, and then COVID hit. There was really hard to do studies in groups of people, so I deviated from the original design. I ripped the Vive sensor subsystems out, and I added in a bunch of other kinds of sensors I thought were more interesting for individual applications. To be honest, like you could do the the Vive stuff is actually pretty easy to integrate to any system that you have. There are a couple like open source software GitHub repos that allow you to get location of any device that just has a near infrared diode, if you have the Vive infrastructure built into your room. So you could kind of use that to figure out the location of any device equipped with that diode. But for right now, I think fine grain location is not really something I'm interested in. And also for building applications, just getting rough RSSI, like signal strength measurements, is good enough to figure out if you're in a room or not. But exactly where in the room you are, I don't really care too much about it. There's also a privacy question there that I often get asked. Do we really want to know where a specific user is at all times? And I would argue no. But it depends on the use case. So.
And when you're saying RSSI, is the idea that you understand every Wi-Fi router in a building, and so you're understanding the signal strength that the glasses have to that router, or are they like Bluetooth mesh, or what's the idea there?
Yeah, I mean, there's a couple ways of implementing it. With Bluetooth, you could have a couple base stations in each room and stuff that transmit data to like a local server. And depending on how far your glasses are from the individual border router, then I mean, you can kind of parse that out just by getting the RSI measurements between each border router and the connected nodes, and you're able to know roughly what proximity a device is. I know that like Nordic with their NRF52 line of chips, they do something a bit more complicated where they're able to use 2.4 gigahertz to get even finer grain location of a user. But still, if you're in a cluttered environment, just relying on RSSI for fine grain localization is difficult, but you can at least figure out if someone is in a room. That's good enough. So that's kind of what I'm interested in. For building applications specifically, all I care about is if you're in a room or if you're not in that room. But yeah, you would have to rely on other infrastructure. So.
Nice, thanks. Yeah, if any, I mean, I actually have some more questions as well, but if anyone has any questions, feel free to ask. Okay, well, I have a question for Alex. I'm curious, so when you first started working on smart glasses a while back,
Yeah.
with the telescope and then even moving into the open source smart glasses, what use cases were you most interested in, either in building right away or also maybe in a longer term? Like if you had kind of a holy grail pair of AR or all day wearable data glasses right now, what kind of use cases would you be interested in using?
Well, okay, so for me, it was mostly for the, flashy, interesting factor of the hardware itself. But probably like my number one use case, like something that I wanted to achieve, but still haven't, for one reason or another, is basically being able to get information from my car on my smart glasses using a Bluetooth ODD2 reader. Being able to pull in any sort of speed, RPM, and honestly, what would be great would be, I'm blanking on what it's called. Somebody built a tool for this, and I wish I could remember the name, but essentially it would analyze Google Earth and get the angle of road curvature at various points, and being able to predict the curvature of essentially blind turns before you go through them.
I predict the curvature of what? Sorry?
Of roads. specifically for like blind turns, like in like mountainous Colorado roads.
I see. Interesting. Cool. There's another question in the chat from Javier. I think for Patrick, wondering how much it costs to build the sensing glasses, aside from assembling, and also if there's any way to buy a ready-made pair.
That's a great question. So all the design files are open source for Captivates. AirSpecs are incoming. We're going to be publishing a paper on them soon, especially after this study. So if you when you're building anything electronic, there's manufacturing at scale, right? So if you're building a one-off, then it's going to be a little pricey, because we're using two rigid PCBs, and then also we built a flex circuit that runs through the front of the glasses, and the setup cost of a manufacturer to kind of set up their tooling for all that stuff can be a couple grand. So if you want to just build a one-off, it'll probably cost you around 2,000, and that's including parts and manufacturing. But if you want to build 100 of them, then that quickly drops to about $200-300 per part. So it's a bit of a loaded answer and question a little bit, but yeah, at scale you're looking at maybe like 200. But if you're building a one-off, probably 2,000.
Cool, thanks. Hopefully that answers your question, Javier. I see another question from Ismail. Ismail, maybe you could explain a little more what your question is about. I'm not sure what you're asking, but you could feel free to unmute and ask, or if you want to just elaborate a little bit. Anybody else? Any questions from anyone else? We're kind of moving into the area which is more of an open discussion, so we can keep this Q&A up and running because it looks like there's more questions rolling in. But also, we kind of open things up a little bit more at the end. So if anyone has anything, like any ideas they want to share, anything that they want to talk about or announce, just feel free to unmute yourself and go right ahead. Mark is asking if you were able to explore flip phone hinges to Patrick, and was your solution based on a ribbon?
Yeah, actually, flip phone hinges were one of the first things we looked at. So we did buy a couple flip phones in China and took them apart. And the circuitry actually going through them is pretty simple. There's just a flexible PCB and FPC cable kind of going through. And that's kind of what we did in the last design, although there are a few caveats. So I wrote a whole paper on this, and we published it in 2020 in the IMWT journal. But in short, our flexible PCB, it's 4 layers in the front, and then the little ends that go through the hinge, it's 2 layers. So it's a special kind of flexible PCB that goes from 4 layers to 2 layers, and that way there's less stresses on the PCB, that the part of the PCB that experiences dynamic bending. So the glasses are made to last. But yeah, a lot of our, I guess, current design has been inspired by flip phone hinges.
Yeah, that's pretty cool. Actually, just recently I was reading Meta put out a article about how they built the Ray-Ban stories, and I was reading that, and they filed a patent for a new way. They're also using a FPC, flexible PCB, but they developed a new way to do it, and they filed a patent. And it's one of those things, you kind of almost don't want to go read the patent, so you have, you don't get the idea from it. But it's interesting how everyone developing these, it's a major roadblock for, for some glasses, they're just going rigid, and like you said, it's not really too reasonable for mobility and travel, where it goes from taking up a little pocket to taking up your whole backpack kind of thing, without a hinge. So I see some more questions. Jason is wondering if for Alex and Patrick, if there are plans to mass produce these projects, so people have access to the hardware, which is probably an interesting question for two different open source teams. But what do you think?
Okay, I'll go first. On the open source smart glasses front, definitely not. Mass manufacturing is really not our goal. We kind of want to make an open source design, and this is what we've made. All the files are on GitHub. You're free to make your own, modify it to your liking, but you will probably not be seeing it on your local Target store shelf anytime soon.
Yeah, I think for me, originally we weren't going to do that, and then we got to a point where we wanted to do that, and then COVID hit, and the supply chain got all screwed up, and then we decided not to do that. But the short answer is I don't know. So right now I'm producing 20 of the AirSpecs, and there are already a handful of researchers that are going to be using them for their research. So I'm going to be supporting them. But I could see something if there is enough interest, especially for some of the med schools I've been talking to, that they could pull together funds across different people. That then it becomes economical for me to produce like 100 of them, and so that I don't have to handle some of them myself. We could, but for mass production, like for a consumer grade version, I don't have that in my timeline right now. But I guess we'll see.
Fair enough. I have another question, Patrick, and you actually got into it a little bit. So I was wondering about, without the display, what is the modality for human input, and what is the plan for how a behavior is going to be modified based off of what are the results of the sensing, and how is behavior going to be modified? So I saw the app, and I see, like, it seems like you actually have a pretty nice UI going on there. And so maybe even more on, if you could talk more on the side of, you were mentioning like gases, maybe you notice gases and you try to do things a little bit differently in your cleaning routine. But if you're thinking about like some use cases, and if all the engineering challenges were solved, what kinds of things how would you want to change behavior, or what use cases do you envision?
Yeah, so for a lot of the things that I'm interested in, I don't necessarily need a display to alert the user, at least immediately. So I don't necessarily need a display in their field of view, but we all have, a lot of us, most of us have cell phones, a lot of us have smartwatches, and so what I didn't show was that we have the app. We also have an Apple Watch secondary app that we're using, so we're push notifications if there are any kind of environmental signals that are beyond the health limits, and so we are notifying you that way. Surprisingly, though, just having the two LEDs that could change color that face towards the person's eye, if we subtly change them based on changing CO2 values in a room, people pick up on that. And then they will use that to condition themselves and to kind of reflect back on why are the gas measurements increasing? What is going on? And then you could kind of use this for, like, one example is a classroom, right? You're in a classroom, you close the doors, there's 30 people in there. Within 30 minutes, you can see the CO2 concentration go from 400 parts per million to like 2,000 parts per million. And so that alone is interesting, but no user can actually sense that, right? Not like naturally. They could feel that it's stuffy, but they don't really know why it's stuffy. And so having a pair of glasses with this like slight, like lightweight actuation mechanism, and then having the app where they could actually just open up and get a more detailed view is the way that we see a user interacting with our system. Yeah.
Cool. And in terms of the concerts, what was the idea there? Did we lose Patrick for a second?
Uh-oh.
Oh, there he is. Yeah, Patrick, I just asked, as an extension to the use cases, you were talking quite a bit about music and concerts. And what would that use case kind of look like from a user perspective?
Can you ask that again? Sorry, I dropped out.
Yeah, no problem. Just we're talking about the use cases for the sensing glasses, and a few times you mentioned that concert scenario. And so, what do you think from a user-centric perspective that would look like at a concert?
Yeah, so if you're ever at a concert, you often could see people that are like really resonating with the music. They're bobbing their head along, they're kind of moving their bodies, and so just that alone, just having just a simple IMU, measuring that and giving that data to the performer, I think is great, right? Because the performer can actually tune their music to elicit a specific response, right? And what you can also do is you're not only measuring the users, but now that the performer has some kind of quantitative measurement of the users, they can then start actuating specific users or specific regions of users by the LEDs alone. So kind of like messing with people's attention. I'm doing a lot of like immersive kind of visualization. So like there's PixMob, for instance, which you often see at like large stadiums where it's just a bunch of LEDs that users hold on their wrist or have equipped on their wrist. And you can do like these like scattered visualizations. So that's kind of what I'm seeing with that I would like to do with the glasses. But I guess it really depends on if we're going to do a crowded like a group application again. I mean, it's a bit of a pain to hand assemble 20, 30 of these while also trying to balance with PhD. So
Yeah, no, definitely fair enough on the last point. But so it would be, so on one hand, it's actually using them as actuators, as human input. But then also from what I understand, you might actually be providing the artist or the DJ with live insight into how people are vibing so that they can kind of have a live feedback loop of how to change their music or what style or tempo is resonating, and kind of like a closed loop feedback system for the musician.
Yep, exactly.
Nice, very cool. I like that a lot, and I think there's a lot of potential. We've looked at that a bit with EEG as well, where you have an audio evoked potential and kind of how intently is somebody actually listening to what's going on, or probably with the glasses, the IMU would be a good indicator there because of how synced with the music are they in terms of movement.
Yeah, although EEG would be difficult if you're in if you're like at a concert venue and you're sweating, the
Yeah,
signal is going to go just crazy.
yeah,
So,
definitely. You're headbanging and moving around. It's definitely noise would be a big issue.
yeah.
Awesome. Well, we're pretty much at the end here, and so thank you so much, everybody, for joining this meetup. This was super interesting. I definitely enjoyed the presentations and hearing more from Alex and Patrick at the end. And it's great to see some new faces here. Welcome anybody who's new. I think I see some names that I've heard but haven't seen here. Farbot, I think, is from Monocle, right? From Brilliant. Oh no. There's multiple Farbods, I guess.
It's a similar sounding name. I spoke to him once on LinkedIn. No, we look a bit alike, I guess. But
Yeah,
not the
maybe.
same one.
Yes. Well, sorry, but welcome anyway. And there's just one final announcement I'd like to make, and then we can break it off. So we've been seeing lots of growth in terms of the meetups. These started really this is only the fifth one, and it started just a few months ago with just a few people, and it's been growing every time. And so as we're growing as a community, we're kind of trying to engage more and bring in more people. And as that happens, we could definitely use help in terms of many different things. So from article writing to work on the website, to building relationships with people in the industry, to helping plan and run these meetups. There's all kinds of opportunities to become involved. And so if you're interested in helping out with the H20 SmartGlasses community and helping us grow, please reach out to me and the team and shoot us a quick message, because we could really use everyone's help to make the community thrive, basically. So anyway, thank you everyone so much for joining. Thank you, Alex. Thank you, Patrick, for the presentations. That was very interesting and fun. And everybody, please, jump on our smartglasses.community website and click the big join now button, because that's where we send out our meetup invites every month. And so, yeah, thank you so much for joining, and I'm looking forward to seeing everybody at the next one. But bye for now. Have a great weekend. Thanks for joining. Bye, everybody.